Before we talk about square roots, let's talk about perfect square numbers. We know what a square is. It's a figure that has 4 right angles and 4 congruent sides. It's the area of the square that attaches the geometric representation to the idea of a perfect square number. The area of a square is its length times its width. So if this square has side lengths of 3, then its area is 3 times 3, which is 9. Does that make sense so far? Okay, good. So now let's talk about what a square root is. It's related to a square. What if we want to know what the square root of 9 is? What that means is we're going to take 9 unit squares and arrange them to make a larger square. And if we do that, we'd like to know the side lengths of the larger square. Since the side lengths are 3, the square root of 9 is 3. So while a perfect square number tells us something about the area of a square root of a number tells us something about the side lengths of a perfect square. Let's try another one. What if we'd like to know what the square root of 4 is? Well, that means we're going to take 4 unit squares and arrange them to make a larger square. The side lengths of that larger square are 2, so the square root of 4 is 2. Now let's generalize this a little bit more. What if I tell you we have a square and its area is x squared? Well, that means the side lengths of the square are x, so the square root of x squared is x. So can you see how squares and square roots are related to each other? Perfect. Let's keep going. Now we've already said that the square root of 9 is 3. We knew that because 9 was 3 times 3, which we could also write as 3 squared. Thinking of the prime factors of that number under the radical sign, that number is called the radicand, can be really helpful in finding the square root of a number. So what if we want to know the square root of 196? We would need to know the prime factors of 196. You might remember finding prime factors by making a factor tree. So 196 is 2 times 2 times 7 times 7. Now if we look at those factors in the radicand and try to pair them up, 2 times 2 is a pair of 2's, and 7 times 7 is a pair of 7's, we can find the square root of 196 by multiplying the 2 times 7 to get 14. That makes sense because 14 squared is 196. We can also choose to write those products using exponents, and while that may not be too helpful here, it becomes really helpful when we're looking at radicands that have variables in them. How about the square root of 1089? Well, our factor tree tells us that 1089 is 3 times 3 times 11 times 11. And if we look for pairs of factors, 3 times 3 is a pair of factors, 11 times 11 is a pair of factors, we can multiply the 3 and the 11 to get 33. That's the square root of 1089 because 33 squared is 1089. Again, we could choose to write that radicand using exponents if we found that to be helpful. Now let's get back to a radicand that has a variable in it. We said that the square root of x squared is x. So how do we find the square root of x to the 6th power? Well, one way to do it would be to say that x to the 6th power is 6 factors of x. And every pair of x's will give us part of our square root. So we have 1, 2, 3 pairs of x's, and x times x times x is x to the 3rd power. So the square root of x to the 6th power is x to the 3rd power. While that makes it really clear that we're pairing up these like factors, it takes a long time to write all those factors out. It would be nice if we could go straight from the beginning to the end. And actually we can. That's because the 6 in the exponent tells us we have 6 factors of x. And to pair them up, meaning put them in groups of 2, we can take 6 and divide it by 2 to see that that gives us 3 pairs of x's. And that 3 is where we get the 3 on the exponent of x to the third power. All that means is there's 3 pairs of x's in x to the 6th power. That's a handy trick to know when we're trying to simplify a radicand with variables in it. How about this one? The square root of a to the 12th, b to the 4th. Since we're trying to pair up those like factors, we can say that the 12 factors of a would give us 6 pairs, and the 4 factors of b would give us 2 pairs of b's. So the square root is a to the 6th power times b to the 2nd power. Sometimes the radicand is not a perfect square. 8 is not a perfect square because we can't take 8 square units and form a square out of them. So what do we do if we're trying to simplify the square root of 8? Well, we're still going to look for pairs of factors in the 8 that are the same. And we can do that the same way we did with the other problems. We can take the 8 and make a factor tree out of it to find the prime factors, rewrite that 8 as 2 times 2 times 2, and then look for pairs of factors that are the same. We do have a pair of 2's that are the same, but that other 2, well, it's just kind of a leftover factor that can't be paired up. So it's going to remain underneath that radical sign. So the square root of 8 is 2 times the square root of 2. So you can see that in simplifying a radical expression, we can always use the same approach. We can just take the radicand, find all of its prime factors, and then look for pairs of prime factors that are the same. If we have a pair of prime factors, fine, that's a perfect square. Anything that can't be paired up is not a perfect square, and so it'll remain inside the radical. So the square root of 75 is 5 times the square root of 3. If the radicand has variable factors, then let's just work with the powers. X to the 8th is 8 factors of x. And we could group those 8 factors into 4 groups of pairs. So the square root of x to the 8th is x to the 4th. The y to the 13th we could group into 6 pairs with 1 left over. The 6 pairs of y give us y to the 6th, and the 1 leftover factor of y remains part of the radicand as the square root of y. So x to the 4th, y to the 6th times the square root of y is the simplified form of our original radical. One last example. How about the square root of 16 x to the 9th, y to the 4th? That's a combination of number factors and variable factors. Well, everything we've talked about still applies. We know the square root of 16 is 4 because 4 times 4 is 16. The square root of x to the 9th, well, let's see. 9 divided by 2 is 4 with a remainder of 1. So we have 4 pairs. That's x to the 4th, 4 pairs of x's, and a leftover x that remains in the radicand. And then y to the 4th, okay, 4 divided by 2 is 2, so that gives us 2 pairs of y factors and no leftover y factors. So the simplified form is 4x to the 4th y squared times the square root of x. So there you have it. It's really just the start of what we can do when we're looking at radical expressions. We'll look at more later on, but for now, this is a good introduction.